Hello. So let's get started so that we'll remain on schedule. We'll start in 1 minute. Okay, so let's get started. It is a pleasure to introduce Gilad. I think many of you know he has been a regular speaker at the MUG for, I don't remember how many years, but X number of years.
The only question if I beat Dan or Dan beat me.
Okay, I don't know. So I have to do some bookkeeping and see. Yeah, okay. So I don't want to, Gilad always tells me don't read it. But just I'll read the first few lines. He's the Senior Vice President of Networking at Nvidia. And he serves also as the chairman of the HPC-AI Advisory Council Organization and the president of the UCF Consortium and ... Okay, okay. So today he will be talking about the Nvidia HPC networking platform. So let's give a very big welcome to Gilad.
So is it fixed or Dan still broke it? Oh, fixed. Just wanted to make sure. So thank you for leaving the coffee break and orange juice. I'm gonna talk about stuff that we develop and work on. Obviously, if you have questions, feel free to stop me throughout the discussion. No need to wait till the end. It's dangerous place here. There's so many cables around here. So trying to make sure you don't fall. So being part of Nvidia, came from Mellanox. After 20 years around at Mellanox, focusing on the networking side, and then become part of Nvidia. And I think it's well, at least for me, a great journey. From Nvidia side of things, we actually don't look on components when we start developing something. We look on the entire data center. We build data centers. Data centers has become the unit of computing. You know, in the past, the CPU was the unit of computing, and then you bought units of computing and so forth, and then the server became the unit of computing. Now the data center is the unit of computing. So we build data centers, starting from applications down to the software frameworks, the SDKs, and then all the elements that you need to bring in, the compute portion, the communication portions, and so forth, and building an entire platform. Now, we don't just design the platform, we actually build those platforms for NVIDIA usage, for our own research, for our own development. We build systems that are in the top 10 of the top 500 list, for example, internally. And we use those systems to develop new software, to develop new applications, to develop the next generations, and to do our own research on them. And this is actually gave us a great opportunity to look on the entire data center and so forth. The network piece is becoming more and more important. And I think Dan talked a little bit about that. If the data center is becoming the unit of computing, then the network actually defines the data center. The way that you connect the different elements in a data center is actually going to define what the data center is going to do. And we develop several network platforms actually that define a data center is to become a different data center. We have platforms. We have the Ethernet platform, for example. I'm going to start with that, and then I'm going to go to the InfiniBand side. We develop an Ethernet platform that we call Spectrum X, that is built with a combination of Spectrum 4 switch and Bluetooth 3 DPUs. Actually, there is no way to build a network infrastructure which is not end-to-end, so that's why we call it a network platform. And in Spectrum X, or with Spectrum X, we develop actually a new kind of Ethernet, a new class of Ethernet. We develop a class of Ethernet for AI. And that class didn't exist before Spectrum X, actually. So we develop an Ethernet platform, a new class of Ethernet platform that is aimed for supporting AI communications for AI clouds. And for people that needs to or wants to build AI clouds, that they need to use the Ethernet ecosystem. They want to use the Ethernet ecosystem for the software services, for example, and so forth. We develop a new class of Ethernet that can serve their needs. So Spectrum X now is moving into production, and you're going to start seeing that as the networking building block for some of the AI clouds out there. And now, AI clouds also went into transition in a sense, because AI clouds brought a new element into clouds. Traditional clouds didn't support distributed computing. Most of the workloads in clouds were kind of a single node, maybe even a single GPU. But Gen AI created a transition in clouds that need now to support distributed computing, and distributed computing is a completely different animal. And therefore, we needed to create a new class of Ethernet that supports those AI clouds and actually be a bit element that defines the data center as an AI cloud. InfiniBand is another platform that we develop, and InfiniBand is the gold standard for large-scale AI, what we call AI foundries. Systems that are built to support large-scale applications that can go to tens and hundreds of thousands of GPUs, for example, supercomputers, scientific computing, and so forth. We create also a good synergy between InfiniBand and NVLink. So NVLink is the connectivity that we use for GPU to GPU to create kind of a larger virtual GPU entity, to be able to have GPUs share their data in their memory in that sense. So things that we develop for InfiniBand, we start also bringing to NVLink, and things that we created in NVLink, we also brought to InfiniBand, and actually creating synergy between those two. One example is doing data reductions on the network. We developed data reductions on InfiniBand, and now we're bringing actually data reductions to run also on NVLink. So the next generation of multimode NVLink also supports Sharp within NVLink. So now you can actually do data reductions between the GPU to GPU communications, and then when you go to InfiniBand, you have the data reduction when you do the scale out. So we have the InfiniBand platform and the combination between InfiniBand and NVLink becomes the gold standard for large-scale AI. AI factories, for example, large-scale scientific computing. And then our Ethernet platform, or new class of Ethernet platform, actually creates the ability to build Gen AI clouds, for example. Now, building the compute and the network also gives us the opportunity to move algorithms between the elements. So there's algorithms that traditionally were run on CPUs or GPUs, but they're probably much better to run on the network, so we actually move them to the network. There are algorithms that runs on the network, but can be much more effective actually to run closer to the memory, closer to the CPU and the GPU, so we move those algorithms there. You can think about it as CPU or GPU can be an extension of the network, or the network can be an extension of a GPU or a CPU in that sense, and you can move algorithms between those two sides. Going more details on the InfiniBand platform. So obviously InfiniBand is a network, so you need to support all the network elements. RDMA, which is one of the key elements, ability to bypass overheads on CPUs and GPUs in a sense, and moving data directly to the host memory or the GPU memory. Some people confuse ROCE with network latency, or RDMA with network latency. RDMA does not do anything related to network performance in a sense. It does with reducing overheads and reducing memory copies and stuff like that. You can run ROCE on a very slow network and still have RDMA. But ROCE or RDMA, those are the elements that are critical in order to avoid buffer copies. So this is one area. Second area is, of course, doing all the elements around optimized routing within the network, adaptive routing and congestion control and so forth. We start fusing AI algorithms with congestion control, for example. Because congestion control, it's a more complicated algorithm as the system growing in size, for example. And there is a lot of smartness in how you control injection rate into the network as part of avoiding hotspots. So we actually created AI algorithms as part of the congestion control mechanisms and so forth. In-network computing also becomes more and more interesting, or more and more important. Actually, the in-network computing is an extension of the GPU or CPU into the network itself. We start with doing data reductions, and we extending the data reductions to other elements. We created a device that's called DPU, Data Processing Unit, or Bluefield, that actually bring more computing into the fabric. And the fabric becomes a computer, completely computer by itself. And I'll talk a little bit about that. So from the InfiniBand devices themselves, there are compute engines that runs on the switch, and they run on the switch in hardware, on the switch ASIC itself. And that's for doing small message reduction and large message reduction. I'm going to show you some of the performance benefits of that. ConnectX-7, the NIC side, it has all the offloading that comes with InfiniBand. And there is several elements of in-network computing on the NIC itself. But then going to the DPU extend those in-network computing to also add programmable. And there are two programmable engines that runs on the DPU. One of them sits on a data path with an MMU, and the other one is based on multiple ARM cores and memory that sits next to the DPU itself to make the DPU actually a full computer by itself. So this is an example of Sharp, of doing data reductions on a switch. There is a new set of results with Hopper GPUs, by the way, and also Sharp running on NVLink. I'm not presenting it here yet, but if someone is interested to see the impact of Sharp on NVLink and InfiniBand with Hopper GPUs, just catch me in one of the breaks. So this one shows nickel or reduced performance. I don't know if it does work. So there are two results here. The dashed lines looks on nickel or reduced without using Sharp. And the different ones here is increasing number of GPUs. The one in yellow, it's 128 GPUs, and then going all the way, the green line is 128, 1K GPUs. So as you have more and more GPUs, it takes bigger and bigger message sizes in order to get to kind of the full wire speed that you can do without the data reductions on the switch. The dashed line, sorry, the solid line, this is the InfiniBand performance with Sharp. So first you get the same performance level regardless of how many GPUs you use, which is important. The second thing is that you get a constant number here, and it's around 1.7x compared to not using that. So running data reductions on a switch hardware enables to reduce the amount of bandwidth that you need to send by almost a half, and you get a 1.7x performance increase on nickel or reduced operations. On ConnectX-7 or Bluefield 3 and Quantum 2, we're seeing similar numbers, and actually there is a nice boost because we actually running Sharp both on NVLink and on InfiniBand. So we're improving the performance there even further than this capacity. Adaptive routing, I mentioned. Adaptive routing is two elements. And adaptive routing, essentially adaptive routing is something that you need to run end to end. You cannot do just adaptive routing on a switch. You cannot just do adaptive routing on the NIC. It needs to be an end-to-end if you're building an AI or an HPC network. Reason is simple, and I can take an example from Ethernet side, because this is what we did on Spectrum X. In the Ethernet world, there was multiple tries just to do adaptive routing on the switch side. But then it created problems. If you want to do fine-grained adaptive routing, meaning doing packet by packet adaptive routing to do full packet spreading, you will need to deal with out of orderness, because data will come out of order. And if you want to try and fix that out of order on the switch, you need to have deep buffers on the switches. And if you have deep buffers on the switches, you create long tail latency, and long tail latency just kill your performance. If you don't have deep buffers, then you cannot do fine-grained adaptive routing. This is where you do flowlets, kind of you do flow by flow. So this is an example why adaptive routing cannot just done on the switch. What we do with InfiniBand or in Spectrum X is running adaptive routing end to end. So the switch does the fine-grained adaptive routing, packet by packet adaptive routing, and the element that creates back or fix the out of order and put things back in order is actually the NIC, the endpoint, or in the DPU or ConnectX in that case. So the NIC or the DPU put things back in order, and does it back in order directly in the host memory or the GPU memory. So there is no buffer copies. It's direct memory placement, and with that you can do a very nice fine-grained adaptive routing. Adaptive routing now run by default in many of the systems out there, and definitely on the systems that we build. Second thing that also become more and more interesting now as systems grows in size is the ability to change routing real time and do that by the switch or the switch network itself. In cases where link goes down, it could be because cable goes down or link flapping and so forth, you want to change routing and change routing quickly. We created capabilities between switches that obviously identify there is a link issues, but then create communications, in-band communications between switches around them, so those switches will avoid those routes. Now that's what we call shield. In a sense, switches will repropagate information about changes in cable conditions, for example, or health of connections, to the place where other switches can actually change the route and avoid those areas. So this is another thing that helps to keep systems up and running and keep jobs up and running, even if there are any failures within the network itself. So going into the DPUs, the DPUs or data processing units were created to support different kind of applications. One of the things that we are using the DPU for the aspect of scientific computing is to overcome some of the long-term bottlenecks. The first thing that we wanted to look into solving or helping with is overlapping. The ability to improve overlapping between computer and communications, and actually using the DPU to become the MPI processor in that sense, or be responsible for all communications. Second thing is improving load imbalance issues and reducing jitter. And we all know, if there is a single slow node in the system, the entire application is being slowed down. And many of the reasons, many reasons for that is because CPUs are busy or GPUs are busy, and they cannot participate in a multi-process communication because they are still busy. By moving those communications to be run on DPUs, we actually run those on elements that are not busy on running workloads. So we can progress MPI algorithms, even though CPUs might be busy, and with that to be able to reduce the load imbalance issues and to eliminate jitter impact. There's also elements around multi-job performance and making sure that one job running in a system will not impact another job running in the same system. So that's also something that we do with DPUs by controlling injection rates into the network. So the DPUs, just if someone is not in the details of what the DPU is, the DPU is a device that actually replaces the NIC on one side. It includes the full NIC functionality, but beside of the NIC functionality, it also includes programmable areas. Nvidia Bluetooth 3 includes which is the latest Bluefield device, or the DPU device, includes the full ConnectX-7. So it's a PCI Express Gen 5, 400 gigabit per second NIC, full RDMA, and all the stuff that I've talked previously on. And it also includes two computation areas, or two programmable areas. One of them is a 16 cores MMU, 16 cores, processor that sits on the data path with an MMU that can do quick things on data when it goes in and out. It can generate packets, it can change packets, it can perform different kind of data algorithms on packets that goes in and out. And there is another programmable entity which includes 16 ARM cores and a DDR5 memory that can do much bigger things. The DPU or the ARM cores are running Linux, so essentially you get a full computer in that device, and that computer can do very interesting things. One of the applications that DPU serves is running the infrastructure, running the data center operating system. For example, running the virtualization, running the hypervisors, running the storage access, running everything that's related to the infrastructure. And that becomes a de facto element in all the cloud infrastructures that we see. Because when you build a cloud environment, security is one of the most important things. And therefore you want to separate between the infrastructure domain and the application domain. In the past, the infrastructure domain was running on the same CPUs that running the applications, and if a guest OS takes ownership of the CPU, it takes ownership of the entire infrastructure. And the answer for that, or the solution for that, is to move the infrastructure domain to run on a separate entity that does not run the users, and that's the DPU. So today, DPU is running, for example, VMware. They're running other containers, other virtualized environment. Every large cloud actually uses DPUs today. Either their own or they're using from Nvidia or from someone else. So that was the first application. Second application is to be able to accelerate storage. DPU, as a PCI Express device, can emulate itself to be any other PCI Express device. In particular, DPU can emulate itself to become a flash device, a local flash device, which means the application sees the DPU, it's like unlimited storage, unlimited flash. And when DPUs actually get flash commands, you can translate them to a remote flash command and send them to a disaggregated storage, get a response, and then translate it back to a local flash response. You can add to that the ability to do compressions and decompressions and aspect like that. So it's a great storage device, essentially, storage accelerator. The third one is taking the DPU into what we call the east-west network, or the compute network. You know, the east-west network, you can do interesting things. For example, you can make the DPU becomes the MPI owner or the MPI processor, and actually control MPI communications. We started with doing collective communications and making the DPU be responsible for the collective communications and the progress of collective communications. But you can extend it to point and so forth, and actually use the DPU just as a communication device, the full communication device. There is other elements are being developed on the DPU, which probably discussed in different times. Now, in order to make it easy, because you don't want to open the DPU for the user to just access the DPU freely, we created a framework or an SDK that's called Docker. Docker, it's similar to CUDA run on GPUs. That's the SDK that runs on the DPU. And everyone that wants to create a service on the DPU can actually create that service using that SDK. And then that service can be placed in a secured way on the DPU. So the DPU can be completely isolated from the users on one side that's running on the server, but on the other side, they actually run services and support. So we brought services for UCC for collective operations and bringing services for UCX for point-to-point. For example, one of the things that DK went to teach, working with Envapage team is to put an Envapage service there. So now you actually can have a specific Envapage service runs on the DPU and so forth. storage, there is security services, encryption services, and many other services that you can plug into Docker, and that will be offered on the DPU. So one of the projects that we're doing on the DPUs or developing on the DPUs for MPI, as I mentioned, Enrich, which is sitting there, he has a lot of responsibility in that area. So kind of presenting some of his results. I'm kind of taking the glory. So sorry. The idea on running MPI on the DPU is actually creating processes or agents running on the DPU, and then processes that running on CPU or MPI process running on a CPU can communicate to the processes running on the DPU and asking the DPU to actually perform that work. In a simple way, if you have process on the host, that process can communicate to an agent running on the DPU, asking the agent on the DPU to perform a data movement. And then from that point, the agents on the DPU will work or communicate between themselves. So one DPU can access another DPU or communicate to another DPU to perform local RDMA operations, remote RDMA operations, and so forth. So the DPU can manage the entire iterations or the entire work. And then once done, then the DPU will indicate to the host processor that the work has been completed. In this approach, you can move anything. You can move all-to-all operations or gather operations, any collective operation, for example, as well as point-to-point. And if you have collective operations, then DPU can start talking with other DPUs completely across entire systems and actually moving the data, even though CPUs might be busy or GPUs might be busy. So that's actually reducing the load imbalance problem. So some examples of results, looking on all-to-all V numbers, there is one PPN and there is full PPN on the right side, probably much more interesting. But we can see that also with blocking elements, also with blocking operations, there is a nice reduction in latency by actually moving the operations to be completely managed on the DPU. If we're looking on non-blocking operations, the impact is much greater. So now actually at 4 nodes, we're cutting latencies in around half and so forth. And obviously, if you're using non-blocking operations, you can also achieve nice overlapping between computer and communication. Now, previously, lots of people tried to achieve good overlapping between computer and communications by using some of CPU cores to running MPI. So for example, if I have 60 cores on a CPU, I can take 8 cores aside to running MPI and keep the rest to run the application, to run the workload, and with that to be able to achieve overlapping. The problem with that approach is that on one side you can achieve overlapping, but on the other side you're going to reduce the performance of the workload itself, because those cores are still competing on the same memory I/O that the other cores that running the applications are using. So that actually didn't help. But having the DPU with its own memory and not taking anything from the CPU capabilities, now we can actually achieve overlapping and improving application performance. So you can get both worlds here. So this is on the DPU. There is other elements that we're developing on the DPU. I mentioned previously congestion control, and I'm gonna let you a little bit about that before going here. I think I have a few more minutes to go. Right? Wrong? Oh, I'm out. Okay. So one more minute on that. So we can talk about congestion control if someone is interested, one of the breaks. There is another element that we are working on, which is related to utilizing of telemetry information in order to bring predictive maintenance into data centers. Data centers are obviously growing in size. And growing in size, there is more components in the data centers. And there is more opportunity for elements to fail. One of the things that we wanted to help with is doing predictive maintenance, to be able to foresee failures before they actually happen. The way that we're doing that, and this is a big project within Nvidia, we're starting with some elements. We have some elements working today, by the way, and then we're going to extend it to the entire data center itself. The first focus was looking on cables and trying to foresee cable failures in the future by collecting telemetry information and then doing analysis on performance of cables over time. You need to create correlations to temperatures, to workload, and so forth. So there's a lot of information that you collect. There is the SDK, so we brought actually plugins that actually do that analysis. They're collecting telemetry information, they're looking on the cables, on paid cables, they're giving indications of performance changes over time, and they're managing the entire connectivity there. That element actually can give nice predictions of several days before something can go down. So we started getting predictive maintenance in order to fix elements before they go down. Last, and sorry for taking that last minute. InfiniBand continued to move in a very fast pace. And we're looking on around pretty much 2 years between generations, give or take. Less than 3 years between generations. NDR is already in production for quite some time. It's 400 gigabit per second end to end. Next one is going to come. This is an IBTA roadmap, so I can actually put it there, and kind of show you where things are moving. Next speed is going to go to 800 gigabit per second XDR. So if NDR was out, production, you can look on the time frame. You can actually estimate when XDR is going to be out, which is not that far from now. So we're going to move to 800 gigabit per second across the network end to end. Generation after that is going to go that and double, and then there is a future defined here, which we expect IBTA to announce that not far away, announce that in a short future, in a sense. Next one actually going to double that, so every generation double the bandwidth and add more capabilities. So again, today we're at 400 gigabit per second. Looking forward to move not in too long from now to 800 gigabit per second speed across the network, and then you see the speeds after that. Sorry for taking a few more minutes. Thank you very much for listening.
No worries. We do have a question from the online chat. Speed up by DPU with non-blocking communication is understandable. Wondering why blocking communication is also seeing a speed up.
Rich, do you want to answer that? I can drink my coffee.
I can take it away.
Just briefly, with an asynchronous agent, you can detect things that you can't without an asynchronous agent, and so we change an algorithm to improve the performance based on that.
Even though a blocking element, you need to run it after you finish the compute, then running the blocking elements. On the DPU, we can change the algorithms of MPI to make it a little bit more effective, to better utilize the network access or the network for actually doing the full algorithm. So that's why also for blocking scenario, we can still reduce the latency.
Hello. So thanks for a very informative presentation. My question is, since DPUs are becoming so powerful, and if we consider a use case of multiple workloads running on the same node or multiple users running on the same node, and they are all funneled through one DPU, so can you create multiple instances of DPU processes so that each user is assigned to one such instance and have their own quality of service, and they are not interfering the communication or whatever the computations you're doing on the DPUs, so they don't interfere with each other?
Yeah, the DPUs become more and more powerful in a sense. Bluefin 3 versus Bluefin 2, there is like 4x increase in compute and 4x increase in memory I/O. And Bluefin 4 will take it to another level and so forth. The DPU provides services. So obviously when you're running multiple processes or multiple workloads on the host, each of them gets services from the DPU. You don't need to physically break elements, but essentially the DPU can virtualize itself and provide different kind of services for different kind of workloads in that part. And that's the reason, by the way, we are increasing the capabilities of the DPU. Having quality of service on the network, you can get quality of service on the network in that sense. Quality of service on the DPU, it's not really needed in that perspective because you actually provide different kind of services, or you can split the services to the workloads that are actually running on the same infrastructure. So we do a quality of service, but the DPU does not need to have that. Actually, you have enough services on the DPU to support workloads, multiple workloads running on the endpoint.
Thank you.
Do we have any other quick question from the audience?
I understand we're running a little late, but I think you explained that with your DPU, you can get a much better performance in terms of the network activities, right? But that's only on the network side. At the system level, to materialize such benefits, you have to be able to assume that your CPU is running quite busy while your DPU is taking care of all those network stuffs, right? If your CPU cores are sitting there idling, then that benefit coming from the DPU may not be quite materialized at the system level. And I think that depends on the application domain. So my question is here, by adding the DPU into the system, especially per node, that adds the cost and the power, right? So do you have any the data or the thought on the application domain that takes most the benefit out of the DPU, even though when it adds the cost and the power to the system?
Yeah, it's actually a good question. So first, DPU does increase power, obviously, because you have cores running there and so forth. But you can also shut down those cores. Meaning, if you don't use the DPU to the full capacity of it, and you just need a subset of the elements of the DPU, then you can shut those down. Actually, those are dynamically being shut down. So it actually reduces the power of the DPU itself to what you need to use. And if you don't use the ARM cores at all, then actually it shut down the entire compute element, and you just have kind of a NIC from the DPU. So it doesn't consume more power than what it's supposed to consume. You can also, this is one of the capabilities that we are bringing in. You can also do power cap on the entire network, by the way. So this is something that didn't exist in the past, but you can power cap the network, and the network will perform up to that power and will not go beyond that. If you run some workloads that need, for example, less network, but you want to maximize the power on CPUs or GPUs because maybe you're running a specific benchmarks that you want to do. Okay, this is for this element. Now, it's true that if you have workload that don't consume the entire cores on a CPU, then you have cores left that you can do something with them. But those cores cannot do the same things of what the DPU can do. Okay, the DPU is not a DPU because of the cores that exist there. DPU is strong for the workload that it was designed for because it has specific hardware engines around those cores that helps the DPU become much better for specific workloads. For example, the DPU is an optimized infrastructure processor. And it's not because it has cores there, because you can do the same things on a CPU, but because it has specific hardware engines for doing encryptions and compressions and decompressions and other elements that you need for the infrastructure processing that doesn't really exist on a general purpose CPU. Now, back to specific to your question, let's say that you build a cloud environment, for example, right? You need to run the infrastructure on the DPU because of security reasons. So even if your CPU cores are not fully utilized, even if you have some cores are empty, you probably don't want to run the infrastructure on the CPU because that's a security issue. That's a security issue. So you want to actually use the DPU even if you're not using all the cores on the CPU. Now, in that case, I would actually shut down those cores on the CPU, kind of, save power and stuff like that. But you don't want to run the infrastructure workload on the CPU because of that, because in this case, you're back to a security issue. The same things for MPI and other stuff like that. You can do the MPI elements on a CPU. Will it be as effective as on the DPU? The answer is not, because the DPU actually runs much closer to the network. So you can do things much closer between DPUs, and you don't need to go over PCI Express to the CPU in order to do those operations, and again go back over PCI Express back to the network to do that, right? So you still want to run those workloads on the DPU because it's going to be much faster to react, much faster to operate versus using the CPU there. Now, if you constantly don't use all the cores on the CPU, then you might want to buy something with less cores and save some money, right? Kind of building the right infrastructure.
Yeah, well, can we do it quickly, real quick?
So as you move this kind of functions in DPU, which CPU can do, there is still some added latency of, rather than doing CPU from the local memory, you're moving to some other DPU memory. So what's the impact of that latency on the workloads or application?
Yeah, that's a good question. First, the DPU accesses the host memory directly. It doesn't go through the CPU. You can access it directly and so forth. When you send data over the network, meaning when you do multi-process operations, you're going to go over the network anyway. Now, the question is how much I can do still within the network instead of going multiple times over PCI Express to the memory, right? I can do things on the CPU as much as I can and then minimize the use on the network, or I can maximize the use of the network and try to minimize the access to the host memory. If I maximize the use on the network itself, I might be able to do things faster than doing that on a CPU. And obviously, if the CPU is busy, then that's even more important. So this is why we're doing that approach. Now, we have memory on the DPU itself, so you can do a lot of work within that DPU infrastructure itself, and then minimize how many times you need to go over PCI Express to the host memory. In any case, you need to do that, right? Because you're going to move data from host memory to host memory, you will need to do that path. But we're minimizing that path, and we're doing a lot of work within the infrastructure itself, right? So, for example, a process running on a CPU, we say, okay, I need to do some multi-process work with that specific amount of data. The DPU doesn't need to copy that, so you can actually completely move the data, runs the multi-process operation, then do the response back. It's going to be the same number of times going over PCI Express, but now you can do it much faster. And you can do that, obviously, in parallel if the CPU is doing other stuff. So overall, you don't see an increase in overhead. Actually, you're seeing improvement performance. That's why you saw the improved performance even with blocking operations, not just with non-blocking operations.
Thank you. Let's give a hearty hand of appreciation for the great talk to our speaker.